So this is Chapter 3, Section 6 on variation. And there's three types of variation we're going to go over. They're direct variation, indirect variation, and I think joint variation is the term that they use for a combination of both. So to be honest with you, the very first type of direct variation you're already aware of. It's another word for it might be linear variation. So we'll look at the definition. Y varies directly as x. So you have two variables, y, and y is going to vary as x varies, or y is directly proportional to x. If there exists a non-zero constant k such that y is equal to kx. So you've seen this before. If y is equal to mx, you should already think that's the equation of a straight line through the origin of slope m. And the only thing that they've done now is they've changed the variable m to k, where k is the constant of variation. So the slope in this very first case, what we've known as the slope, is now called k, and it's the constant of variation. So how do we solve problems in direct variation? So first we have to determine what type of variation is in question, and literally the problem will tell you. The problem will say something like directly proportional or varies directly. Those are clues that tell you that we're dealing with direct variation. So literally the type of variation is gleaned from carefully reading the problem. So the first thing we do, really the only thing that we have to find out is what the constant of variation is in each case. So we're given a specific case, we solve for k, and then with new information we take that k and we solve for y. So we write the general relationship amongst the variables as an equation. Use k for the constant. Listen, people, if you want to use m for the constant, use m for the constant. It doesn't matter. It's a dummy variable. Substitute given values of other variables to solve for the unknown value, which is k. That's what we'll use, because that's what the book is using. Substitute the value k into equation given in 1 to get a specific formula for the variation problem, and then substitute the remaining values and solve for the unknown asked in the problem. So let's do it. So the area of a rectangle varies directly as its length. So here here's our general formula. Y is equal to our constant of variation times x. And that means y varies directly as x. Now in this case, what is it that varies directly? A varies directly as the length L. So sometimes you can just come over here and say, let area equal y and length equal x, or you can replace the y and the x in our kind of guiding formula with another variable of your choosing that stands for something that reminds you of what it is. A capital A for area, a small l for length. So that's our major formula. So let's just do A is equal to K times L. Or if you're more comfortable, do Y is equal to k times x with this guide up here. So if the area is 50 meters squared, so literally I'm going to do something here. I'm going to put the units in just once. So 50 meters squared, that's what the m squared stands for. When the length is 10 meters, find the area when the length is 25 meters. So the first thing we do right here is I have to find the value of k. So the reason I put the units in, normally we don't, but some of you who go on into engineering or physics or something that uses units all the time, the units are really, really important. Now you don't have to use the units, but they kind of let you know what's going on. So we're going to solve for k. So k is my unknown, so I'm going to divide both sides by 10m. So that's 50 meters squared divided by 10 meters is equal to k. And the reason I did that is I don't want weird sounds coming in, is because I know k is going to be in terms of meters. So 50 divided by 10 is equal to 5. M squared divided by m is 5m. So k is equal to 5m, and m in this case means meters. Now I'll go back and I'll do this again where I don't worry about the units. But the point is, units are good guides to know you're doing something right. So here is my little rectangle thing. I'm actually connecting the sides. So this is my length and this is my height. So given a length and a height, I have an area. Now this in here is an area. So its area is equal to length times height. So if the length is in meters and the height is in meters, then the area is in meters squared. So that already tells you that our k, our constant of direct variation, needs a unit attached on it. And that's all that we're going to do. But I found that my k is equal to 5m. So let's go back and let's solve the problem. I will do this another way, and I will drop the units. So now we're getting ready to do the second part. So I have my equation. A is equal to 5m times L. So how did I get that? I was solving for k, and I found that k is equal to 5m, and I just replaced k with 5m. So now it says find the area when the length is 25 meters. So our length is given to be 25 meters, and I'm going to put the meters in here too. So that's equal to 5 times 25 times meters times meters. So that's equal to 125 meters squared. And that's our answer. And having the meters squared in there tells you that you're on the right track, because you know that the area is given in square units, such as square feet, square inches, square meters, square yards, etc., square miles. So that's a little check. So let's do it without worrying about any units, and we'll literally just start y is equal to kx. We'll say let y equal my area, and I will say let x equal my length. Then we're given that from the formula, if the area is 50 meters squared, when the length is 10, is that what it is? Yes. Find the length, or the area, when the length is 25. So the first thing I'm doing is I'm just solving for k. So 50 divided by 10 is equal to k. So my constant of direct proportionality is 5. So I found my k value. So now I go back up and I replace it in the general equation, and I have y is equal to kx, which is 5x. And then it says if the area is 50, find the area, so y is what I'm looking for, when the length is 25. And we immediately get y is equal to 5 times 25, so 5 is equal to 125, and that's our area. But there isn't any units. I dropped the units, right? So you just have to realize from the units, this is 125 meters squared. And we don't write meters squared. We're really lazy, and we do 125 m squared. Okay. So that one's really not hard at all. You've been doing that all along and you didn't realize it. So now we're going to direct variation as an nth power. So it's exactly the same as variation, except our exponent n on the power of x is greater than 1. So the base equation is y is equal to k times x to the nth. Now this is something you've seen also, but it's not a linear equation, is it? My paint has been added to your favorites. So y is equal to 5x squared. Well, you know what the graph of that looks like, right? You know the graph of y is equal to x squared, what that looks like. So when I do y is equal to 5x squared, for example, 5 is greater than 1. So this results in a narrowing of the graph vertically. So we've seen this before. It's just getting a different name, and our exponent n can be any integer greater than 1. So actually, direct variation is the nth power. If n is equal to 1, then it's linear, and if n is greater than 1, then it's non-linear. And we do the exact same thing when we solve our problems. So let's just look at another example. Oh, I don't even give an example. So you will be given examples. Let me just make one up. Let's say y varies directly as, let me not make one up. You'll get to see these in your homework and you can solve them. I don't know, I'm pretty sure the reason I don't have, the thing is I don't want to make one up and do it in my head and just make it a disaster. I could, but I would like the numbers to come out really nicely. So I'm pretty sure in our actual book there were no examples given, and that's the reason I don't have any examples. And direct variation is pretty simple. What they want to immediately get you to is indirect variation or inverse variation. So in this case, n has to be greater than 0. We say y varies inversely as the nth power of x or that y is inversely proportional to the nth power of x if there is a constant not equal to 0, such that for all x we have y is equal to k over x to the n. So if n is equal to 1, then we say y varies inversely as x. So where it varies inversely as x, or varies inversely as the nth power of x. Let's just do some problems. In a certain manufacturing, so remember our base equation here is y is equal to k times x to the n, and our first step is always going to be use the information to find the value of k, and then I have a formula, and then use the information in the second part to solve for y. In a certain manufacturing process, the cost of producing a single item varies inversely as the square of the number of items produced. So in this case, we're just going to keep the same variables. Y is going to stand for our cost. If you want to let y be equal to c, that's fine. And our x is going to be equal to the number of produced items. So what is our exponent? Notice it says item varies inversely, so I know I should be using this type of a formula. Well, it says as the square, so our number exponent n is equal to 2. So here we go. If 100 items are produced, so that means x is equal to 100, each cost $2. So I have to find the value of k. So that's not going to be too bad. Notice maybe that's 100 squared. So that means 2 times 100 squared is equal to k. I'm just solving for k here. So that means k is equal to 20,000. So we always find the value of k. So now that we've done that, it says find the cost per item. So again, we're looking for the cost per item, which is y. If 400 items are produced. So I use my base, I use this formula now. Y is equal to 20,000 divided by x. So we're going to solve for y. And how many, or what's the number of produced items? 400. So in this case, our y is equal to 1/8. This has to be squared. And kind of getting ahead of myself. So I'm thinking about, I don't want you to use a calculator. So that's 20,000 divided by 160,000. And you always know the trick that when you're dividing things that have trailing zeros, each zero can be canceled out. So that's equal to 2/16, which is equal to 1/8. And so y is equal to 1/8. And in this case, that's 1/8 of $1. And 1/8 is about, well, actually, exactly 0.125. So the cost is approximately equal to 13.13 of $1, or 13 cents. But I'm not quite done with this problem yet. In this case, it's far more customary in mathematics to use function notation and to say that cost is a function of produced items. And our base equation, instead of being y, we would say c of x, that's a cost function, is equal to k over 100 squared. And once we solve for k, we would have a cost function given by the cost per item, that's what x stands for, is equal to 20,000. Oh, there should be a squared there. Glad I saw that. 20,000 divided by x squared. So yeah, I'm glad I actually went over that, because that I failed to write the exponent there. And that's important that you write. So let's look at another example. So now we have joint variation. So basically we have just one constant of variation, and that's all we ever have to solve for, is that constant of variation. So here's the example. Let m and n be real numbers. Then y varies jointly as the nth power of x and the mth power of z, if for all x and z there exists a k not equal to 0, such that y is equal to k times x to the nth times z to the nth. And all of the information, nothing's really more difficult than anything we've ever done. We just have to find the constant k and find the values of n and m. They will then give us enough information to find k, and then with that information it's really just plug and chug to find the rest. Literally, this is an interesting type of a function. I'll talk about the function notation for this after we do this. So our base equation is y is equal to k times x to the nth power and z to the mth power. So the area of a triangle varies jointly as the lengths of the base and the height. So guess what? A triangle with base 10 feet and height 4 feet has area 20 feet squared. So in this case, y is triangle area. X will be the length, and z will be the height. And that's it. Our n value is equal to 1, and our m value is also equal to 1. If it had been otherwise, they may have said the volume, say, of a triangle, that doesn't really exist, varies jointly, well, not in the sense that we understand it, varies jointly as the lengths of the base squared and the height cubed. So if the base squared, then my n value would be 2 and my m value would be 3. But here it's just as the lengths of the base and the height. So I have y is equal to k times x times z. So I have to find my k value. So length of base, there we go. X is the length of the base. So now let's take what we're given and find k. So, and y is the triangle area. So a triangle with base 10 feet and height 4 feet has area 20 feet squared. So let's find the value of k. Well, all I have to do is divide 20 by 10 times 4, which is 40, and that's k. So k is equal to, we want to simplify that, so k is equal to 1/2. And if you know the formula for area of a triangle, this makes sense. Because you know the area is equal to 1/2 times base times height. So here, in this case, they've used h for height, we used z, and they used b for the length of the base, and we used x, and they used a for the area, but we used y. So now that we have that, what are we given? Find the area of a triangle whose base is 3 feet and height is 8 feet. So y is equal to 1/2 times base is 3 feet and my height is 8 feet. So y is equal to 3 times 8 divided by 2, which is equal to 3 times 4, which is equal to 12. And this is 12, and what is our area? These are feet, so it's in feet squared. So you could leave the unit on there and you would find how much, you would find naturally the units at the end. So the addition of units in mathematics, we try to keep things unitless, but when all of your math is applied math, like in physics or in engineering, then the units are almost always left on there. So for those of you who are going into physics or engineering or even biology, where the units are important, you will learn how to leave them on the mathematical calculations there. So how would this look like if we used function notation? So my k is 1/2 times x, y. Well, this is a function in 2 variables. So we have a notation for that. And since our function is going to be in terms of area, we'd say area, and I wrote down the formula wrong. Did anyone see what I did? That should be z. We'd say our area is a function of my x value and my z value, and it's equal to 1/2 times x times z. So this shows you we can easily extend our function notation. In this case, I have 2 independent variables, x and z, and they are my inputs, and my output is the area. Or if you want to use it, the regular function notation, f of x z is equal to 1/2 x times z. Or if you want to use area is a function of base times height, area is a function of base times height, and it's equal to 1/2 b times h. And I'm giving to you to that now. Some of you have to do calculus all the way to Calc 3, and in Calc 3 you will encounter functions of 2 variables. Is that it? I believe that is it. That is it. So pretty basic when it comes to variation.